Hi there. Thanks for joining us again. This is Space Nuts, where we talk astronomy and space science. My name is Andrew Dunkley, your host. Coming up on this episode, we'll be answering audience questions. Ash is looking at Apollo 13. Daryl is asking questions about absolute zero, which seems to be a common topic. I'm pretty sure we've had this one pop up previously, so we'll have a crack at that again. Obviously, we didn't do it well enough before. And Alex is focused on anti-gravity. That's all coming up on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Joining me to solve all of those riddles and puzzles is Professor Fred Watson, astronomer at large. Hello, Fred.
Hi, Andrew. How are you doing?
Now, Fred, let's go to our Q&A segment. This is where we basically take questions from the audience, which are always welcome. Don't forget to send them in to us. And we endeavour to answer them, or we just pretend we know the answer and then move on. And I mentioned at the beginning that Ash wanted to ask a question about Apollo 13. That's not quite accurate. What he was asking about, he used Apollo 13 as an example of a situation that he doesn't quite get. Let's hand it over to Ash.
G'day, what I want dunks. Ash here from Brisbane again with another question for you. I was recently watching the movie Apollo 13 with my daughter, and coming towards the end of the movie where they're talking about the re-entry of the command module, the news reporter said that too steep an angle and it will burn up on re-entry. I get that. And then he goes on to say that come in too shallow and the spacecraft will bounce harmlessly off the atmosphere, floating off into space, skipping off the atmosphere like a rock off a pond. I don't really get this one. Skipping off the atmosphere, is this something we've observed in the past? Is it just something theoretical? I'm interested to hear your thoughts on that. Love the show, guys. Keep it up.
So Ash is bringing up an interesting point, because we all understand the implications of coming in too steep and hitting the atmosphere and burning up. We've seen that in recent years with disastrous effects and the loss of lives, unfortunately, on one particular occasion. But we don't think much about the bouncing off thing, and I've always just taken it for granted that that's gospel. And I suppose he brings up a very solid question as to, have we ever witnessed this? Let's try and understand the concept a bit more. Bouncing off the atmosphere like a skipping stones across a lake.
And I think that's the problem, Andrew, that we kind of use what I think is the wrong terminology. I mean, we've all seen skimming stones, where you skim across the lake, exactly as you've said, and that's what this sort of thing conjures up for you in your mind. But what you're actually doing is it's the angle of entry that is the critical thing. If you get it too shallow, too steep, then the velocity that you come in at is too high for the spacecraft's heat shield to cope with the frictional heat that you've got as it passes through the atmosphere. Because remember, the atmosphere is just getting steadily more dense as you go down. And so that's catastrophic, as you've just said. And so then there's a sort of sweet spot where you can use the friction of the atmosphere to slow you down, atmospheric braking. It's a balance between all the thermal construction of the heat shield, how much temperature that will withstand and for how long, and how much of that heat is conducted through to the interior of the spacecraft. So that balancing act is very much a sort of, it's judging many different factors: steepness, temperature, the resilience of the spacecraft heat shield, all of that, to get the right angle of entry. So, but if you then change that to make it shallower, remember you're still in a gravitational situation. I mean, when the spacecraft is outside the atmosphere, basically the only force acting on it is gravity, and that dictates its motion exactly. So when it enters the atmosphere, that's when the thing is going to start slowing down. So if you enter at an angle that is too shallow, the gravitational pull of the Earth, which the thing is feeling and it's going downwards, it will also, as it hits the outer parts of the atmosphere, it will basically feel the deceleration of the atmospheric braking, but there won't be enough if you're not at a steep enough angle. There won't be enough gravitational braking, and eventually, even though the heat shield will heat up and everything, but eventually it won't actually come down to Earth. It will keep going through the upper atmosphere. Its orbit will be altered dramatically. In fact, it may even, as a result of that, go into orbit around the Earth because it's experienced some braking, but it's still not being captured by the Earth in the sense that you want it to be. You want it to come in at this. It's actually in about 11 kilometers per second. It's got to get hit the Earth's atmosphere to slow down enough to come back in from the moon. Okay. So it's not a bounce. It's that gravity wins over atmospheric braking. And what would happen, as I said, it's likely that it would come out of the atmosphere, but now be in an elliptical orbit around the Earth. And so its orbit, depending on just what the circumstances were, might turn into a long ellipse and go back down. Now, there have been...
contrary to popular belief, you're not going to be speared off into oblivion.
Well, you would be, basically.
Oh, okay.
Because you'll be in the wrong orbit and you don't have any means of changing the orbit. You're probably still...
Let's say a spacecraft does make that mistake and gets sort of bounced off. Is it recoverable if you've got the power?
Well,
if you've got an engine, surely you can...
Yeah. But they didn't have. That's a command module. It's basically an inert lump of metal with a...
Oh, you're right. Yeah,
shield.
Apollo 13 was. They only had one shot at it. Yeah. I mean, with something like a space shuttle or the secret space planes and all those things, they've got their own power, so they would be able to potentially recover. I should qualify something I said earlier. I said we've seen this happen with people involved in that terrible space shuttle tragedy. They actually had the angle right, as far as I'm aware. It was a failed tile that caused the craft to burn up. So it wasn't actually the wrong angle and speed, because it did actually re-enter. It just re-entered cataclysmically.
Because there were gaps in the wings, which were caused by damage incurred on launch.
Damage on liftoff, I think it was. Yeah.
So, but the shuttle, Andrew, on re-entry is not powered. And you might remember it's got 3 huge rocket motors on the back, but it also has a huge fuel tank to feed them. So they can't actually run those motors on re-entry. It was an inert lump of metal for re-entry that turned into a glider. Apollo, of course, had parachutes. So what I was going to say was that we've had several instances of asteroid samples being dropped to Earth by spacecraft. OSIRIS-REx is the most recent one that comes to mind, because you remember its content of asteroid sample from Bennu were dropped in Utah last year. It took them a long time to open the capsule, the canister this year, because they had a bolt that was stuck. But that was dropped by OSIRIS-REx, is a mother spacecraft. It dropped the sample capsule and then went on its way. And I would guess that it was close enough to Earth when it dropped that to be within at least the outer layers of the atmosphere. And so those calculations, that physics would have been very precisely done so that the spacecraft, perhaps it did need some braking to put it into a new trajectory, because it's on its way to a new satellite now. Sorry, a new asteroid now to investigate
Yeah.
that. So yeah, complicated answer, but and bouncing is the wrong word, but it certainly in a movie it's as good a word as any to use.
Yeah. Never let the truth get in the way of a good story, Fred. That's what they always say. But it was a good question to ask because it sort of cleared up what probably a lot of us misinterpreted in terms of bouncing off the atmosphere.
Yeah,
So,
yeah, good question.
yeah. Thank you very much, Ash. Now, we've got a question from Daryl, and our brains tell us that we have sort of come across this type of question before. And Daryl's in South Australia. This question is from a long-time listener who is also a patron. So thank you, Daryl. I think we've had a few patrons sending questions lately. Why, in a universe of such extremes and vast emptiness, does absolute zero, 273.15 degrees Celsius or 459.67 degrees Fahrenheit, even exist? Given that a star is thousands to millions of degrees, why is there a limit on cold temperature? Is there a limit on hot temperature? Absolute hot. And while I'm in the question asking mode, is there an absolute heavy and an absolute light? Keep up the adequate job, Daryl. Thanks, Daryl.
Yeah, so Daryl's point is well made. Certainly, absolute zero has a physical meaning. It's not just a random temperature. It's the temperature at which atomic motion stops. So, on the level of atoms, all motion stops at that temperature because temperature is the motion of atoms. And depending on how hot you are, the faster the atoms move. Is there an absolute hot? Probably not. It's, things happen, atoms fall to pieces at various temperatures. We don't know whether some of the fundamental particles of the universe fall to pieces at certain temperatures. It's very likely they don't. I think I'm probably right in saying that the hottest temperature ever reached in the universe was in the Big Bang, where we were talking about maybe even hundreds of millions of degrees. But I don't think there's a barrier to more, to more extreme temperatures in terms of the upward temperature rather than the low temperature. Absolute heavy, probably a black hole. We've got black holes that are up to 4.5 billion solar masses now, and that doesn't seem to have a limit on it. We can't, we're going to find ones that are even more massive than that. So you can't say there's a limit on mass either.
Wow. What about an absolute light?
It's probably nothing, isn't it, really?
Yeah, well, that's what I was thinking. Yeah.
Empty space.
As Monty Python said, nothing comes from nothing.
Yeah. Trouble is, it's not true. Well, that's the story of the universe. In the beginning was nothing, and then it exploded.
Yeah. Yeah. Very true. So yes, no, and no. Daryl? Vic, in terms of all those absolutes. And thank you for your question. Let's move on to our final question for this week. And this one comes from Alex.
Hello, Alex Marshall from London, UK. Yes, I'm from the States, Indiana to be precise. Question I have is dark energy, more appropriately invisible energy, anti-gravity? Space not expanding, but that it's pushing back against the gravity of each one of the galaxies, and that it's hovering around the outside of a galaxy is what makes the gravity work stronger for a galaxy. I'd love to hear the answer. I'm sure we don't know exactly what dark energy is, but is that something that's being looked at?
Okay. Thank you, Alex. So the question was, is dark energy anti-gravity?
It is tempting to think of it in those terms because it's a repulsive force pushing things away. Much.
My wife says I'm one of those too.
Yeah. Oh, she's probably on the money there, Andrew. You know? But it doesn't behave anything like gravity. That's the reason why we don't think it's basically anti-gravity. Its behavior is quite different. It seems to be uniform throughout the universe, whereas gravity hangs around anything that's massive. Basically, any object with mass generates gravity. Even you and me. So there you are. There's the opposite pull for your wife.
Oh, I hate to say it, friend, but wait for it. That's heavy.
Thought I'd give you an opportunity to use that one.
Yeah, well, you sure did.
Yeah. So gravity behaves in a well-known, well-understood way, even though we really don't know what it is, but we know very precisely how it behaves. And what we're working on is similar precision to know how dark energy behaves. And you might remember our discussion about the equation of state last couple of weeks ago, which is basically the number that astrophysicists use to identify how dark energy behaves. But it seems to behave the same everywhere. It may be something that evolves with time, but by and large, it doesn't relate to objects. In other words, it doesn't relate to matter. So its behavior is very much different from gravity. And it's a property of space itself. That's the bottom line. If you took all the matter out of the universe, you'd still have dark energy. And indeed, cosmologists who look at these large-scale galaxy surveys to kind of determine the geometry of the universe, which is what gives you insights into dark energy and dark matter and the various proportions, they see them as quite separate things with quite different characteristics. And so anti-gravity, whilst in a sense it's, as I said, it's tempting to think of it that way because it's pushing stuff apart, but that's not what it is. It's something different, and it's something we don't know and we don't understand. But, Andrew, we're working on it.
We are. I think it's one of the great mysteries of the modern era in astronomy and space science is to solve the dark matter and dark energy conundrums, and they're working on it, but keeps throwing up extra questions, which it's like a formula. You got to break it up into workable parts and figure out every keystone bit by bit until you finally get an answer, and even that might be wrong. That's the problem with it, isn't it? Mm.
Yeah.
Time will tell. How much time, can't tell you. But thank you, Alex.
What is time?
So to answer everybody's questions, yeah, well, that's another thing, isn't it? To answer everyone's questions, the answers were not quite, yes, no, and not really. So that would have done it.
Okay.
Just a reminder too, if you have questions for us, please send them in. Just jump on our website, spacenutspodcast.com or spacenuts.io. There's a couple of links on there, the AMA tab or the little purple button on the right-hand side of the homepage where you can send us your questions in text or audio form. Don't forget to tell us who you are and where you're from, and we'll do our very best to not ever answer them at all, but if we run out of stuff to talk about, we might. No, we will try. We get a lot of duplicate questions, so if we miss you, it's not because we don't like your question or we're too dumb to answer it. We just someone else has probably already covered it, although we did double down on the absolute zero question this week. And while you're on our website, have a bit of a squiz around and see what you can see. Don't forget the Space Nuts shop. You might be someone who buys presents for Easter. There's no Easter eggs on it, but you might find something in there. I mean, Easter does have some kind of astronomical relevance, though, no. Anyway, lots to see and do. And don't forget, if you'd like to become a patron, and if you're a YouTube viewer, don't forget to hit the subscribe button below. That's what we want. More subscribers, the better. And we've certainly got a growing family on YouTube, and they're starting to get really involved as well, which we greatly appreciate. Fred, that's a wrap for this episode. Thank you very much.
Pleasure. See you soon.
Simple as that. Thanks, Fred. We'll see you. And to Hugh in the studio, I wish you all the very best with your editing on that one. But you are an editing magician, unlike myself, who avoids it like the plague. And from me, Andrew Dunkley, thanks for your company. We'll catch you on the next episode of Space Nuts. Until then, bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.